Look up at the night sky. What do you see? Stars, planets, maybe a distant galaxy if you're lucky. But here's the wild part. Everything visible to us, all those glittering points of light, make up less than 5% of the universe. The rest, a cosmic mystery so profound it's kept scientists awake for decades. The bulk of our universe is invisible, hiding in plain sight, and we've given it a name that sounds straight out of a sci-fi novel: dark matter. It doesn't emit light, it doesn't reflect it, and yet its gravitational pull is the invisible hand shaping galaxies, bending light, and holding the cosmos together. If that doesn't send a shiver down your spine, I don't know what will. Think about that for a second. We're surrounded by something we can't see, can't touch, and barely understand. A ghostly presence that outnumbers ordinary matter 5 to 1. It's like living in a house where the walls, the floor, even the air around you are made of something you can't perceive, yet without it, the entire structure would collapse. For all our telescopes, satellites, and supercomputers, dark matter remains one of the universe's most elusive puzzles. But here's the thrilling part: scientists haven't given up. Instead, they've come up with dozens of bold, brilliant, and sometimes downright bizarre theories to explain what this mysterious substance could be. Some ideas sound like they're ripped from the pages of a fantasy novel: particles that only interact through gravity, hidden dimensions, even parallel universes leaking into our own. That's exactly what we're diving into today. Over the years, researchers have proposed everything from weakly interacting massive particles, WIMP for short, to Axions, primordial black holes, and stranger possibilities that defy conventional physics. Some theories have gained traction, others have been ruled out, and a few linger in the realm of maybe, just maybe. So buckle up, because we're about to explore 30 of the most compelling, mind-bending explanations for dark matter. Whether you're a casual stargazer or a hardcore physics enthusiast, one thing's for sure: by the end of this journey, you'll never look at the night sky the same way again. The universe is far weirder, far more mysterious, and far more fascinating than we ever imagined, and dark matter is just the beginning. Let's start with the frontrunner in the dark matter mystery: WIMP, or weakly interacting massive particles. Picture a particle that's everywhere yet almost impossible to detect, like a ghost passing through walls without leaving a trace. That's essentially what scientists think WIMP could be. These hypothetical particles don't interact with light or ordinary matter in any significant way, except through gravity and the weak nuclear force, one of the 4 fundamental forces in the universe. This means they could be streaming through you right now, unnoticed, like invisible cosmic neutrinos, but with far more mass. The idea isn't as far-fetched as it sounds. WIMP fit neatly into existing physics frameworks, particularly supersymmetry, a theory that suggests every known particle has a heavier, unseen partner. If true, the lightest of these superparticles could be stable, lingering from the early universe, making them perfect dark matter candidates. Their predicted mass range is staggering, from about 10 to 1,000 times heavier than a proton, which would explain why they exert such a strong gravitational pull without being directly observable. But here's where it gets even more compelling. WIMP aren't just a theoretical hunch, they align with real-world observations. Take galactic rotation curves, for example. Stars at the edges of spiral galaxies orbit so fast that, according to visible matter alone, they should fling off into space, but they don't. Something invisible, something like WIMP, must be adding the extra gravity needed to hold those stars in place. Despite decades of searching, though, WIMP remain elusive. Experiments deep underground, where shielding from cosmic rays improves sensitivity, have yet to catch a definitive signal. Some detectors have seen tantalizing blips, like the controversial Dharma/Libra results, but nothing conclusive. This hasn't deterred scientists. If anything, the hunt has grown more creative, with proposals to repurpose quantum computers or even use the human nervous system as a detector. Whether WIMP are the answer or just another stepping stone, their story underscores a thrilling truth. The universe is hiding its secrets well, and we're just getting started unraveling them. If WIMP are the heavyweight contenders in the dark matter hunt, Axions are their delicate, almost ghostly counterparts, particles so lightweight they seem to flirt with the edge of existence. Born not from dark matter theories but from an entirely different cosmic puzzle, Axions were first proposed to solve a nagging inconsistency in quantum physics known as the strong CP problem. It's a quirk in the equations governing the strong nuclear force that, if left unexplained, would leave our universe looking very different. The solution: a hypothetical particle so tiny it could slip through the fabric of spacetime unnoticed. Axions are staggeringly light, potentially billions of times less massive than an electron, but what they lack in heft, they make up for in sheer numbers. Picture a cosmic ocean of these particles, rippling through the universe in waves so dense they could collectively outweigh all visible matter. Unlike WIMP, which behave like discrete particles, Axions in high concentrations might act more like a fluid, their quantum weirdness blending into a coherent galaxy-spanning field. This wave-like nature gives rise to one of the wildest ideas in dark matter research: that Axions could form Bose-Einstein condensates, exotic states of matter where countless particles sync up into a single, eerie quantum vibration. Imagine the halo of a galaxy not as a cloud of discrete particles, but as a shimmering, invisible tide. Detecting something this subtle requires equally ingenious methods. Enter experiments like ADMX, the Axion Dark Matter Experiment, which operates like a cosmic radio tuner. Scientists use powerful magnetic fields to coax Axions into converting into microwaves, then listen for faint whispers in carefully chilled detectors. Other approaches, like the International Axion Observatory, repurpose particle accelerators to hunt for Axions produced in the sun's core. Even quantum sensors, designed to pick up the faintest disturbances in electromagnetic fields, are joining the search. The stakes are high because Axions could solve two mysteries at once: dark matter and a quantum conundrum that's baffled physicists for decades. But here's the twist: Axions are so elusive that finding them might require redefining what detection even means. Some theories suggest Axions could subtly alter the properties of light over vast distances, leaving faint fingerprints in the polarization of starlight. Others propose that these particles might cause atomic clocks to tick ever so slightly out of sync. It's a hunt for shadows within shadows, where success could rewrite not just astrophysics, but the very foundations of quantum theory. And if Axions are real, the universe just got a whole lot stranger and more beautiful. Now, let's shift gears to a theory that takes dark matter back to the visible, or at least the barely visible. Meet MACHO, massive compact halo objects. These aren't exotic particles or quantum phantoms, but real, tangible cosmic heavyweights: black holes, neutron stars, even rogue planets too dim to emit significant light. The idea was simple but elegant. Maybe dark matter isn't some new, undiscovered substance. Maybe it's just ordinary matter hiding in the shadows. Picture the halo of our galaxy, a vast, spherical cloud of something enveloping the Milky Way. If that halo were packed with ancient black holes, remnants of the universe's violent infancy, their collective gravity could explain the missing mass. No new physics required. It's a theory with a certain appeal, Occam's razor applied to cosmology. Why invent invisible particles if the answer could be objects we already know exist, just lurking in the dark? But here's where the story takes a turn. In the 1990s, scientists launched ambitious microlensing surveys to test the MACHO hypothesis. The logic was brilliant. If a black hole or neutron star passes between us and a distant star, its gravity should bend and amplify the star's light like a lens, creating a temporary brightening. Teams like the MACHO project and EROS monitored millions of stars for years, expecting to catch these fleeting flashes, and they did, just not nearly enough. The numbers didn't add up. These objects could account for a sliver of dark matter, but not the overwhelming bulk. So why does the idea still linger on the fringes? Because nature loves surprises. Primordial black holes, those forged in the chaos of the Big Bang, not from dying stars, offer a tantalizing loophole. If they exist in a specific mass range, say between 20 to 100 times the Sun's mass, they could evade microlensing detection while still contributing to dark matter. LIGO discovery of merging black holes in this weight class reignited the debate. Could these be the MACHO we missed? It's a long shot, but science thrives on long shots. Until every possibility is ruled out, MACHO remain a stubborn footnote in the dark matter saga, a reminder that sometimes the universe hides its secrets in plain sight. Primordial black holes, cosmic relics from the universe's first frantic moments, offer one of the most tantalizing dark matter candidates. Unlike the black holes we know today, born from collapsing stars, these would have formed when the newborn universe was a seething, ultra-dense soup. Imagine patches of space so tightly packed that they crumpled under their own gravity, collapsing into black holes before the first stars even flickered to life. What makes this idea so compelling is its sheer audacity. Dark matter might not be a particle at all, but a swarm of ancient black holes woven into the fabric of space itself. The mass range for these primordial beasts is staggering, from as light as a tiny asteroid to heavier than 1,000 suns. At the lower end, black holes the size of a grapefruit could be zipping through space right now, their gravity subtly tugging on everything they pass. On the heavier side, objects rivaling intermediate black holes might lurk in galactic halos, invisible yet bending the cosmos to their will. It's this very gravitational footprint that gives them away. When light from distant stars or galaxies warps around unseen mass, a phenomenon called gravitational lensing, some anomalies can't be explained by ordinary matter alone. Could primordial black holes be the culprits? Here's where the detective work gets fascinating. The Ogle Microlensing Survey, which scans millions of stars for telltale flickers, has spotted brief brightenings that fit the profile of intermediate mass black holes drifting through our galaxy's halo. Even more intriguing, LIGO detection of merging black holes with unusual masses too hefty for typical stellar remnants hints at a primordial origin. If these ancient monsters exist in just the right numbers, they could account for dark matter's gravitational grip without invoking exotic particles. But the theory isn't without cracks. Too many small primordial black holes would have evaporated by now, thanks to Hawking radiation, while too many large ones would disrupt star clusters or create lensing events we don't observe. It's a cosmic balancing act, one that keeps physicists debating. Yet the allure remains. If primordial black holes are real, they're not just solving the dark matter puzzle. They're rewriting the story of how our universe began, offering a glimpse into the chaos of existence before time itself had settled into rhythm. While black holes and exotic particles dominate most dark matter discussions, there's another contender lurking in the shadows, one so subtle it barely interacts with the universe at all. Enter sterile neutrinos, the elusive, heavier cousins of the ordinary neutrinos that flood through space undetected. Unlike their better-known relatives, which occasionally bump into matter despite being fantastically lightweight, sterile neutrinos would interact only through gravity, making them nearly impossible to catch. Yet their ghostly presence could solve two cosmic puzzles at once: dark matter's grip on galaxies and a strange excess of X-rays emanating from distant clusters. The key lies in their decay. Imagine a sterile neutrino drifting through space for eons before spontaneously transforming into an ordinary neutrino and a burst of X-ray light. This faint signal, spotted in the stacked X-ray emissions of galaxy clusters, might be the fingerprint scientists are hunting for. In 2014, astronomers analyzing data from the Chandra and XMM Newton telescopes noticed an unexplained X-ray line at an energy of 3.5 kiloelectronvolts, a whisper that matches predictions for sterile neutrino decay. It's not conclusive proof, but it's a clue tantalizing enough to keep the theory alive. Then there's the missing satellite problem. Computer simulations of galaxy formation predict that our Milky Way should be surrounded by thousands of small satellite galaxies, yet we've only spotted a few dozen. Sterile neutrinos could explain this discrepancy. Their unique quantum properties would suppress the formation of tiny structures early in the universe, leaving fewer dwarf galaxies than cold dark matter models suggest. It's a delicate balancing act. Sterile neutrinos must be heavy enough to decay into X-rays but light enough to avoid disrupting larger cosmic structures. The hunt for these phantoms is pushing detector technology to its limits. Experiments like the upcoming fact-check for TTS, Jinping Underground Laboratory in China, or the upgraded fact-check Mini Buani at Fermilab aim to catch sterile neutrinos by their vanishingly rare interactions or distinctive decay signatures. Even cosmic background radiation maps might hold indirect evidence, as sterile neutrinos would leave subtle imprints on the universe's earliest light. What makes this theory so compelling is its economy. Sterile neutrinos wouldn't require rewriting the standard model of particle physics, just extending it slightly to accommodate one more family of particles. But until we capture definitive proof, they remain suspended between hypothesis and reality, a cosmic maybe that could reshape our understanding of the invisible universe. While WIMP and Axions dominate the dark matter conversation, there's another contender that turns the traditional narrative on its head: SIMP, or strongly interacting massive particles. Unlike their weakly interacting cousins, SIMP don't shy away from collisions, they embrace them, engaging in frequent, energetic interactions with each other while still ignoring ordinary matter. Imagine a crowded room where everyone's invisible except for the occasional elbow bump between a few select guests. That's the essence of SIMP. Their social nature could solve one of cosmology's stickiest problems: why small-scale structures in the universe don't quite match predictions. Galactic simulations based on cold, collisionless dark matter produce halos that are too dense at their cores, with far more dwarf satellite galaxies than we observe. It's like expecting a bustling metropolis and finding a quiet village instead. SIMP offer an elegant fix. If dark matter particles scatter off one another, akin to molecules in a gas, they'd redistribute energy, smoothing out those over dense clumps and explaining the scarcity of tiny galaxies. This self-interacting behavior isn't just theoretical, it's hinted at in real-world anomalies. Take the Bullet Cluster, where colliding galaxies left their dark matter components visibly lagging behind visible matter, as if something had slowed them down through friction. Ordinary WIMP couldn't explain that, but SIMP absolutely. What makes SIMP especially intriguing is their potential to bridge particle physics and astronomy. Some models suggest they could arise from a dark sector, a hidden realm with its own forces and particles, interacting only feebly with our familiar universe. Picture an entire shadow universe, complete with dark photons or dark gluons, where SIMP are the equivalent of protons, building blocks of invisible complexity. Experiments like the Large Hadron Collider are now probing these ideas, searching for evidence of particles that could mediate these dark interactions. Yet SIMP aren't without challenges. Their strong self-interactions must be finely tuned. Too weak, and they're indistinguishable from WIMP. Too strong, and they'd obliterate galactic structures entirely. There's also the puzzle of detection. If SIMP ignore ordinary matter, how do we catch them? Some proposals involve hunting for rare particle decays or subtle distortions in cosmic microwave background data. Others suggest leveraging gravitational waves. If SIMP form dense dark stars, their collisions might ripple spacetime in ways we could spot. The beauty of the SIMP hypothesis lies in its audacity. It forces us to rethink dark matter not as a passive backdrop but as an active, dynamic player in cosmic evolution. Whether SIMP ultimately prove to be the answer or just another stepping stone, they remind us that the universe's secrets often defy our simplest assumptions. After all, if dark matter can shape galaxies, why shouldn't it have its own rich, invisible life? Picture a hidden force coursing through the cosmos, an invisible counterpart to light itself. This is the essence of dark photons, hypothetical particles that could be the missing link in the dark matter puzzle. Unlike ordinary photons, which mediate the electromagnetic force we know and love, everything from sunlight to radio waves, dark photons would operate in a shadow realm, enabling dark matter particles to interact through their own version of electromagnetism. It's as if the universe has a secret backup network, humming along undetected while shaping galaxies in ways we're only beginning to fathom. The idea isn't just poetic, it's grounded in compelling physics. If dark matter feels forces beyond gravity, dark photons are prime candidates to carry them. Think of them as messengers shuttling between invisible particles, creating structures and behaviors as complex as those in the visible universe. Some theories even suggest dark photons could mix slightly with regular photons, like two radio stations overlapping on a dial. This faint crossover might be our best shot at detection. When dark photons oscillate into ordinary photons, they'd produce tiny bursts of energy signatures that experiments like the Large Hadron Collider or dedicated dark matter detectors could potentially spot. One of the most intriguing hints comes from an anomaly in the behavior of muons, heavy cousins of electrons. Precise measurements of their magnetic properties don't quite match predictions, and dark photons could explain the discrepancy. If these shadowy particles exist, they'd nudge muons in ways that align with the data. Then there's the mystery of the galactic center's excess gamma rays, a glow that defies conventional explanations. Dark photons decaying into electron-positron pairs might be the hidden culprit, leaving an energetic fingerprint in the cosmos. But the real beauty of this theory lies in its testability. Projects like the Dark Light experiment at MIT and the proposed phaser detector at CERN are hunting for dark photons by blasting targets with high-energy electrons and sifting the debris for anomalies. Others are scouring astrophysical data for skewed light polarization or unexpected energy losses in particle collisions. Even household technology plays a role. Certain types of superconducting cavities can be tuned to ring at specific frequencies, potentially amplifying dark photon signals like a cosmic antenna. What makes dark photons so tantalizing is their dual promise. They could explain dark matter's hidden structure while also bridging gaps in our understanding of particle physics. If found, they'd open a portal to a dark sector as rich and dynamic as our own, a parallel universe of forces and interactions thriving just beyond our perception. Until then, they remain one of the boldest ideas in modern physics, a whisper of something vast and unseen, waiting for its moment in the light. What if dark matter isn't some exotic particle or cosmic anomaly, but an entire mirror universe identical to ours yet forever hidden? This is the mind-bending premise of mirror matter theory. Imagine a shadow world where every proton, electron, and atom in our reality has a perfect twin, identical in every way except one. It doesn't interact with our light, our forces, or anything we'd recognize as ordinary matter. These mirror particles would pass right through us like ghosts, their existence revealed only by the inexorable pull of gravity. It's a concept that sounds ripped from science fiction, yet it emerges from a startlingly simple question. What if the universe's laws are more symmetrical than we ever imagined? The roots of this idea trace back to a subtle asymmetry in nature. When physicists first discovered that certain subatomic processes don't behave identically when flipped in a mirror, a phenomenon called parity violation, it shook the foundations of physics. But what if this lopsidedness is just an illusion? Mirror matter theory proposes that at the birth of the cosmos, the universe split into two sectors, one governed by the slightly broken symmetry we observe, and another where the mirror image rules hold sway. In this shadow realm, left and right are reversed, and particles interact through their own mirror versions of electromagnetism and nuclear forces. The two sectors coexist, layered atop each other like parallel sheets of paper, forever unaware of each other's presence except through gravity's universal handshake. Here's where it gets revolutionary. If mirror matter exists, it wouldn't just explain dark matter. It would render the whole concept redundant, the missing mass haunting our galaxies. Just ordinary stuff from the mirror universe tugging on ours gravitationally. No need for WIMP, Axions, or other exotic fixes. The beauty lies in the numbers. If the mirror sector contains roughly 5 times as many particles as our visible universe, the math perfectly matches dark matter's observed gravitational effects. But how could such a perfectly hidden twin universe emerge? The answer might lie in the Big Bang's fiery aftermath. As the newborn cosmos expanded and cooled, it could have undergone a phase transition, a cosmic fork in the road, where matter and mirror matter crystallized into separate realms. Some theories even suggest that mirror particles could have formed mirror stars, mirror galaxies, even mirror life, all unfolding in lockstep with our own cosmic history, but forever invisible to our telescopes. Detecting this shadow world would require extraordinary ingenuity. One clue might come from neutron stars. If a mirror asteroid collided with a neutron star in our universe, the impact could release a burst of gamma rays with a distinctive energy signature. Other proposals involve ultra-precise experiments measuring tiny deviations in gravity or hunting for particles that oscillate between our world and the mirror realm, much like neutrinos change flavors. The most tantalizing hint might already exist. Certain neutron stars exhibit puzzling cooling rates that mirror matter could neatly explain. Critics argue that mirror matter's elegance comes at a cost. It demands an exact duplication of all physical laws, a symmetry so perfect it feels almost too good to be true. Yet if confirmed, it would rewrite not just cosmology but our understanding of reality itself. We'd no longer be alone in the universe. We'd be sharing it with an invisible twin, a cosmic doppelganger woven into the very fabric of space. The next time you gaze at the night sky, consider this. The darkness between the stars might not be empty at all. It could be teeming with galaxies just like ours, their light forever locked in a parallel dimension, whispering to us only through gravity's silent embrace. Imagine a form of dark matter so feather-light that it behaves less like a particle and more like a cosmic wave, an ethereal ripple spreading across galaxies. This is fuzzy dark matter, a theory that replaces heavy, sluggish particles with ultralight ones, each weighing less than a billionth of an electron. At this scale, quantum effects dominate, turning what we'd expect to be discrete particles into sprawling, wave-like entities. Picture the entire Milky Way's dark matter halo, not as a swarm of invisible marbles, but as a single, vibrating field. A fluid so finely tuned its fluctuations could dance to the rhythm of quantum mechanics itself. What makes this idea so compelling is how neatly it solves one of cold dark matter's biggest headaches, the missing satellite problem. Simulations predict that our galaxy should be swarmed by countless small dwarf galaxies, yet we observe only a fraction. Fuzzy dark matter's wave-like nature smooths out these discrepancies. Because its particles are absurdly lightweight, their quantum wavelengths stretch across light years, preventing them from clumping into the ultra-dense knots that would form excess dwarf galaxies. It's like trying to gather mist into tight balls. The very nature of the substance resists it, but the implications go even deeper. Fuzzy dark matter could also explain why galaxy cores appear less dense than expected. Traditional models suggest dark matter should pile up at the centers of galaxies, creating steep gravitational wells. Instead, many galaxies show a flatter, more uniform distribution, exactly what fuzzy dark matter's wave-like behavior would produce. These quantum waves naturally repel one another at tiny scales, preventing excessive buildup in galactic centers. The result, a cosmic balancing act where dark matter's inherent fuzziness maintains equilibrium on scales both vast and minuscule. Detecting something this ethereal pushes the limits of modern astronomy. One approach involves studying the subtle flickering of distant quasars. As light from these brilliant objects passes through fuzzy dark matter's rippling waves, it should pick up faint, telltale distortions, like a flashlight beam shimmering through underwater currents. Another clue might lie in the precise timing of pulsars, the universe's natural metronomes. If fuzzy dark matter's waves pass between us and these spinning neutron stars, their gravitational influence could alter the arrival times of pulses in ways sensitive radio telescopes could catch. The theory isn't without its critics. Some argue that fuzzy dark matter's ultralight particles would have formed intricate interference patterns in the early universe, leaving observable scars on the cosmic microwave background, scars we haven't definitively found. Others point out that creating such particles requires exotic physics beyond the standard model. Yet the elegance of the idea keeps it alive. If proven, fuzzy dark matter wouldn't just redefine our understanding of the invisible cosmos, it would blur the line between particle physics and astronomy, revealing a universe where quantum weirdness shapes the very architecture of reality. Perhaps the most poetic aspect of all is this. Fuzzy dark matter suggests that the universe's hidden scaffolding might not be made of solid, unseen mass, but of something far stranger, a ghostly symphony of waves vibrating silently in the dark, conducting the motions of galaxies with an invisible quantum hand. Most of the dark matter theories we've explored assume one key thing, that these invisible particles barely interact with anything, even each other. But what if dark matter isn't the cosmic loner we've imagined? Enter self-interacting dark matter, a bold twist on the classic narrative where these mysterious particles don't just drift silently through space. They collide, scatter, and even jostle for position like an invisible cosmic crowd. This idea isn't just theoretical gymnastics. It could solve one of astrophysics' most persistent puzzles: why some galaxies seem to defy the rules of dark matter entirely. Take the case of NGC 1052DF2, a galaxy so baffling astronomers nicknamed it the galaxy without dark matter. By all accounts, this cosmic oddball should be drowning in invisible mass, yet measurements show its stars move as if barely tethered by gravity. Then there's DF4, another ghostly galaxy where dark matter appears to have gone missing. These anomalies don't fit the cold, collisionless dark matter mold, but swap in self-interacting particles, and suddenly things click. If dark matter particles can bump into each other, energy gets redistributed. Over billions of years, these microscopic interactions could eject dark matter from certain galaxies entirely, like a slow-motion game of cosmic billiards where the invisible balls eventually roll right out of the frame. The bullet cluster offers even starker evidence. When two galaxy clusters collided, their visible matter, a haze of hot gas, slammed together and stalled, while their dark matter components sailed right through as expected. But here's the catch: the dark matter didn't just pass through undisturbed. Observations suggest it lagged slightly behind, as if slowed by an unseen drag. That's exactly what self-interacting dark matter predicts. Frequent particle collisions would create a kind of friction, subtly altering dark matter's trajectory. It's a tiny effect, but in a universe where precision rules, even slight deviations speak volumes. So how would these particle collisions work? Picture dark matter as a vast sea of invisible pool balls. In most models, they glide past one another effortlessly, but in self-interacting theories, they occasionally smack together, transferring momentum. The rules of this shadowy game depend on the particle's properties. Some models suggest rare, high-energy collisions, while others propose frequent, gentle nudges. The sweet spot seems to be a cross-section about the size of a proton's width, dense enough to reshape galaxies but sparse enough to avoid collapsing cosmic structures entirely. Critics argue that too much interaction would smear out dark matter halos beyond recognition, leaving galaxies with no gravitational scaffolding at all. Yet proponents counter that nature might have struck a delicate balance, fine-tuning these collisions to explain the outliers without disrupting the broader cosmic order. Experiments like the upcoming Vera Rubin Observatory could settle the debate by mapping millions of galaxies for telltale signs of dark matter's self-interactions, halos that are smoother, puffier, or more misshapen than cold dark matter allows. What's thrilling about this theory is its audacity. Instead of tweaking dark matter's identity, it reimagines its behavior, turning passive spectators into active players in galactic evolution. If confirmed, self-interacting dark matter wouldn't just solve anomalies. It would reveal an invisible universe buzzing with unseen dynamics where ghostly particles don't just fill space, they shape it one collision at a time. Picture dark matter not as a slow, lumbering giant or a speedy, elusive phantom, but as something perfectly in between. This is the essence of warm dark matter, a theory that splits the difference between its colder and hotter counterparts. While cold dark matter moves sluggishly, barely keeping up with the universe's expansion, and hot dark matter zips around at near light speeds, warm dark matter strikes a delicate balance. Its particles are lighter than those in cold dark matter, granting them a bit more agility, yet not so light that they streak through space unchecked. Think of it like the Goldilocks zone of cosmic mysteries. Not too fast, not too slow, but potentially just right for explaining some of the universe's quirks. The secret to warm dark matter's appeal lies in its impact on galaxy formation. In the early universe, gravity sculpted cosmic structures by pulling matter into denser clumps. Cold dark matter's sluggishness allowed it to form tiny, dense seeds that grew into galaxies, while hot dark matter's speed smeared out these clumps, delaying galaxy birth. Warm dark matter offers a middle path. Its particles move fast enough to smooth out the smallest, most problematic clumps, those pesky dwarf galaxies that simulations overpredict, but slow enough to preserve the larger structures we observe. It's like trimming the cosmic overgrowth without uprooting the garden. One of the strongest hints for this theory comes from the scarcity of ultra-faint dwarf galaxies orbiting the Milky Way. Cold dark matter simulations suggest there should be hundreds, yet we've found only a handful. Warm dark matter's slight velocity would have suppressed the formation of these tiny galaxies early on, thinning the herd to match real-world observations. Another clue, the timing of the first galaxies. Some observations suggest stars ignited earlier than cold dark matter predicts. A discrepancy warm dark matter could resolve by allowing structures to form more efficiently at certain scales. But the smoking gun might lie in the cosmic microwave background, the afterglow of the Big Bang. If warm dark matter particles were abundant in the early universe, their subtle motions would have left faint imprints in this ancient light. Experiments like the Atacama Cosmology Telescope are now scouring these microwaves for telltale patterns, hunting for deviations that could betray warm dark matter's presence. Meanwhile, particle physicists are racing to test candidates like sterile neutrinos with specific masses light enough to qualify as warm, yet heavy enough to avoid disrupting the cosmic balance. Skeptics point out challenges, of course. Warm dark matter struggles to explain certain galaxy clusters' shapes or the precise distribution of matter in the universe's large-scale web. Yet its proponents argue that slight tweaks to the model, perhaps mixing in a dash of cold dark matter, could cover these gaps without abandoning the theory's core elegance. What makes warm dark matter so fascinating isn't just its potential to solve puzzles. It's the way it forces us to rethink dark matter as a spectrum, not a monolith. The universe rarely deals in absolutes, and neither should our theories. Whether warm dark matter ultimately takes its place as the answer or merely a stepping stone, it reminds us that the truth often lies not in extremes, but in the nuanced spaces between. Cue balls might sound like something from a sci-fi arsenal, but they're actually one of the most fascinating and bizarre dark matter candidates out there. Imagine a bubble of pure energy, not held together by gravity or electromagnetism, but by the sheer weirdness of quantum fields. These exotic objects predicted by supersymmetry aren't particles in the traditional sense. They're non-topological solitons, stable, tangled knots in the fabric of reality that could have formed in the chaos of the early universe and survived to this day as dark matter. Unlike WIMP or Axions, which are single particles, cue balls are macroscopic clumps, potentially ranging from the size of a proton to that of an asteroid, all while obeying the rules of quantum physics. What keeps these cosmic bubbles from popping? The answer lies in a conserved quantity called charge, not electric charge, but a quantum property tied to supersymmetry. Picture a cue ball as a reservoir of this charge, with its energy density dropping as it grows larger. Up to a certain point, it's actually cheaper for the universe to pack charge into a giant cue ball than to scatter it across individual particles. This makes them absurdly stable, like a cosmic savings account where bulk storage beats retail. Even if a cue ball could decay, the process would take longer than the current age of the universe, meaning those forged in the Big Bang might still be lurking everywhere, invisible and indestructible. The conditions for their birth were almost poetic. In the universe's first microseconds, during a phase transition where symmetries broke and forces split apart, regions of space could have become trapped in a high-energy state. As the cosmos cooled, these pockets might have curled in on themselves, collapsing into cue balls like droplets of dew condensing on a cosmic leaf. Some theories suggest they could have even acted as seeds for the first black holes or inspired the formation of galaxies, their gravitational pull subtly guiding the architecture of everything we see today. Detecting something this strange requires equally creative thinking. If cue balls exist, they might occasionally plow through Earth, leaving behind trails of ionized atoms in their wake. Experiments like the Ice Cube Neutrino Observatory, buried deep in Antarctic ice, could catch these faint signatures. Another clue might come from the depths of old mines, where detectors like the Soudan Underground Laboratory watch for the rare burst of radiation that would occur if a cue ball encountered ordinary matter and unraveled. Even cosmic rays could carry hints certain high-energy particles might be the fallout from distant cue ball collisions. Yet the wildest implication isn't just that cue balls could be dark matter, it's that they'd redefine what dark matter is. Instead of a haze of particles, we might be swimming in an ocean of invisible quantum knots, each a relic from the universe's most violent moment. Their existence would prove that the cosmos isn't just stranger than we imagine, it's stranger than we can imagine, hiding structures so alien they challenge the very definition of matter itself. What if dark matter isn't hiding in the shadows of our three-dimensional world, but in dimensions we can't even perceive? This is the spine-tingling premise of Kaluza-Klein particles, a theory that ties dark matter to the hidden folds of reality itself. The idea springs from one of physics' most ambitious frameworks, string theory, which suggests our universe might have as many as 10 or 11 dimensions, all curled up so tightly we'd never notice them in daily life. But here's the twist: particles trapped in these extra dimensions could vibrate at frequencies that give them mass and stability, making them perfect dark matter candidates. Picture a guitar string, pluck it, and it vibrates at different frequencies, each producing a unique note. Now imagine that string isn't just a musical instrument but a fundamental thread of reality, vibrating in higher dimensions. These vibrations would manifest in our familiar three-dimensional space as heavy, stable particles, Kaluza-Klein dark matter. Unlike ordinary particles, they'd carry momentum in those extra dimensions, making them invisible to our detectors yet capable of exerting gravitational pull. It's like listening to a symphony but only feeling the bass. The higher notes are there, just beyond our perception. One of the most compelling aspects of this theory is its elegance. Kaluza-Klein particles emerge naturally from attempts to unify gravity with the other fundamental forces. In the 1920s, physicists Theodore Kaluza and Oskar Klein proposed that electromagnetism could arise from gravity operating in a hidden fifth dimension. Modern string theory expands this idea, suggesting that particles we know, like electrons or quarks, could have heavier shadow versions if they vibrate differently in extra dimensions. The lightest of these shadow particles would be stable, lingering from the Big Bang as dark matter. But how do you hunt for something that exists partly outside our reality? The challenges are staggering. Kaluza-Klein dark matter would interact so weakly with ordinary matter that even the most sensitive detectors might miss it. Some experiments, like the Large Hadron Collider, hope to spot these particles by smashing protons together at unimaginable energies, creating tiny flashes where extra-dimensional physics might briefly reveal itself. Others search for cosmic fingerprints, anomalies in the way high-energy particles travel through space, or unexpected signatures in gamma-ray bursts. Critics argue that without direct evidence for extra dimensions, the theory remains speculative. Yet its mathematical beauty keeps it alive. If Kaluza-Klein particles are real, they wouldn't just solve the dark matter puzzle, they'd open a doorway to a grander cosmic architecture, where the universe's true nature unfolds in dimensions we're only beginning to dream of. At the very edge of what physics can describe, where the known laws of nature start to fray, lies a dark matter candidate so massive, so elusive, it borders on the philosophical. Planckian interacting dark matter proposes particles with masses approaching the Planck scale, the universe's ultimate unit of measurement. To grasp how extreme this is, consider that a single Planck scale particle would weigh more than a grain of dust packed with the mass of an entire mountain. These behemoths wouldn't just ignore light and matter, they'd barely acknowledge the universe exists at all, interacting solely through gravity's faintest whisper. The elegance of this idea lies in its minimalism. Unlike theories requiring new forces or hidden sectors, Planckian dark matter needs just one ingredient: particles so heavy they're practically frozen in time, relics from an era when the cosmos was hotter and denser than anything we can simulate. Picture the Big Bang's aftermath, a cauldron of energy so intense it could briefly forge these titanic particles. As the universe expanded and cooled, they'd have decoupled almost instantly, drifting into obscurity while leaving behind just enough gravitational bulk to shape the cosmos we see today. No complicated interactions, no delicate balancing acts, just raw, uncompromising mass. Detecting them, however, is another story. A Planckian dark matter particle could barrel through a detector the size of Jupiter for 1 billion years and leave no trace. Their gravitational pull would be infinitesimal individually, relying on sheer numbers to collectively bend spacetime, the only hope of spotting one. Cosmic coincidence: if such a particle ever decayed, a process so rare it might happen once per galaxy per millennium, it could unleash a burst of energy rivaling a supernova. Telescopes like the Fermi Gamma Ray Space Telescope scan the skies for these unexplained flashes, though so far no candidates have matched the profile. Yet the theory's appeal endures because it solves two puzzles at once. First, it sidesteps the fine-tuning problem plaguing many dark matter models. Planckian particles don't need carefully crafted interaction strengths or masses. Their sheer scale makes them stable by default. Second, their existence would hint at a deeper connection between dark matter and quantum gravity, a bridge between the very large and the very small. Some theorists even speculate these particles could be primordial black holes in disguise, or remnants of a higher dimensional reality where gravity behaves differently. Of course, critics argue that invoking Planck-scale physics is like using a sledgehammer to crack a nut overkill for explaining galactic rotation curves. But perhaps that's the point. The universe has never shied away from extremes, from black holes that warp time to quantum particles that defy location. If dark matter truly is Planckian, it wouldn't just fill the gaps in our maps of the cosmos. It would remind us that nature's solutions are often grander, stranger, and more unsettling than we dare imagine. What if dark matter isn't just a sea of solitary particles but forms its own invisible chemistry, complete with atoms, molecules, and perhaps even unseen planets or stars? This is the heart of the dark atoms hypothesis, a theory that dares to imagine dark matter as a rich, structured substance governed by its own version of the forces we know. While most models treat dark matter as simple, lonely particles drifting through space, dark atoms suggest something far more complex, an entire periodic table of shadow elements built from particles that interact through a hidden, dark force as powerful as electromagnetism is in our world. The idea begins with a simple twist on familiar physics. Just as protons and electrons bind together through the electromagnetic force to form atoms, dark protons and dark electrons, if they exist, could unite under a dark electromagnetic force, creating stable dark atoms. These wouldn't just be exotic curiosities, they'd behave fundamentally differently from single-particle dark matter. For one, their interactions would be more nuanced. Instead of slipping past each other like ghosts, dark atoms could collide, scatter, or even form dark molecules, leading to behaviors that might resolve some of the stickiest puzzles in astrophysics. One such puzzle comes from direct detection experiments. For decades, detectors like Xenon and LUX have hunted for dark matter by watching for rare collisions between invisible particles and ordinary atoms. But the signals they've glimpsed are frustratingly inconsistent. Some experiments report potential hits while others see nothing at all. Dark atoms could explain this chaos. If dark matter isn't a single particle but a spectrum of structures, some might interact more strongly with certain materials, creating unpredictable detection patterns. A dark atom's size and composition could mean it bounces off atomic nuclei in ways that defy conventional models, leaving behind a trail of contradictory clues. Then there's the mystery of galactic structure. If dark atoms can clump into complex formations, their distribution in galaxies might differ sharply from the smooth halos predicted by simpler theories. Imagine dark matter, clouds, or even dark dust drifting through galactic halos, subtly altering the gravitational tug on visible stars and gas. Some astronomers speculate that these structures could explain oddities like the Milky Way's missing satellite galaxies or the bizarrely diffuse galaxies that seem to float almost untethered in space. The most speculative and thrilling implication: dark atoms might not stop at simple structures. Given enough time and the right conditions, they could theoretically assemble into dark stars, dark planets, or even dark life. While that's a leap beyond current evidence, the mere possibility hints at a universe far more intricate than we've dared to dream. Experiments are already adapting to test these ideas, with next-generation detectors designed to spot not just particles but the potential fingerprints of something larger. Critics argue that adding a dark force complicates the picture unnecessarily, and without direct proof, dark atoms remain in the realm of elegant speculation. Yet their allure is undeniable. If proven, this theory wouldn't just solve the dark matter riddle, it would unveil a hidden cosmos, buzzing with invisible complexity, where the rules of chemistry play out in a shadow realm we're only beginning to imagine. Now let's dive into one of the most mind-bending twists on dark matter, yet superfluid dark matter. Forget particles clumping in halos. Picture instead an invisible, cosmic ocean flowing effortlessly through galaxies, a frictionless quantum sea that reshapes gravity itself. This theory doesn't just tweak the rules, it rewrites them, suggesting that dark matter might not be a collection of discrete objects at all, but a single, coherent superfluid stretching across the universe. The idea hinges on quantum mechanics' strangest behavior. When certain fluids, like liquid helium, are chilled to near absolute zero, they lose all viscosity, becoming superfluids that flow without resistance, climb walls, and even defy gravity. Now imagine scaling this up to galactic proportions. If dark matter condenses into a superfluid state, its quantum properties could emerge on astronomical scales, creating a unified field that interacts with visible matter not through particle collisions but through subtle collective effects. Here's where it gets revolutionary. Proponents of superfluid dark matter argue that this quantum fluid could modify gravity in ways that mimic the effects of particle-based dark matter without needing invisible particles at all. The superfluid's pressure and density gradients might generate an extra gravitational pull, explaining why stars orbit galaxies faster than visible matter alone can account for. It's like attributing the tides not to the moon's direct pull, but to the ocean's internal dynamics. The result, a universe where dark matter's signature effects arise from a fluid's quantum behavior rather than unseen particles. This theory tackles some of astrophysics' knottiest problems head-on. Take galactic rotation curves. In standard models, dark matter forms a spherical halo around galaxies, but superfluid dark matter predicts a flatter, disk-like distribution, better matching observations of certain galaxies where dark matter seems oddly concentrated in the plane of rotation. Then there's the bullet cluster, often cited as proof of collisionless dark matter. Superfluid proponents counter that the fluid's coherence could allow it to slosh ahead of visible matter during collisions, replicating the observed separation without requiring non-interacting particles. Critics highlight gaps, of course. How does a superfluid maintain coherence across millions of light years? Why don't we see its quantum effects imprinting more clearly on small-scale structures? Yet the theory's boldness is its strength. By unifying dark matter and modified gravity, two historically rival explanations, it offers a third path, one where the universe's hidden scaffolding is both material and ethereal, a quantum whisper woven into the fabric of space. Experiments to test this are as unconventional as the idea itself. Some propose hunting for minute variations in gravitational waves, which superfluids could subtly alter. Others suggest studying the cosmic microwave background for signatures of quantum vortices, twists in the superfluid's fabric left over from the Big Bang. If detected, these fingerprints would reveal a cosmos far more fluid, more unified, and more strangely beautiful than we ever imagined. The allure of superfluid dark matter lies in its audacity. It doesn't just add to the universe's inventory of mysteries, it reimagines the very nature of reality, suggesting that the force holding galaxies together might not be a thing at all, but a state, a whisper of quantum coherence humming through the void. The next time you see a spiral galaxy's graceful arms, consider this. Its shape might not be sculpted by invisible matter, but by an ocean of darkness flowing in perfect, frictionless harmony. Gravitinos are where the esoteric math of supersymmetry collides head-on with dark matter's greatest mysteries. These hypothetical particles emerge from one of physics' most ambitious frameworks, supergravity, blending Einstein's general relativity with the quantum dance of supersymmetry. Picture the graviton, the theoretical carrier of gravity's force, but with a twist, its superpartner, the gravitino. While gravitons mediate gravity, gravitinos would be their heavier, slower-moving twins, forged in the chaos of the early universe and lingering today as cosmic relics. What makes gravitino dark matter so compelling is its pedigree. Supersymmetry proposes that every known particle has an undiscovered partner. Electrons have selectrons, photons have photinos, and so on. The gravitino, as the superpartner of the graviton, sits at the pinnacle of this hierarchy, with masses ranging from a feather-light electron volt to a staggering trillion times heavier than a proton. Gravitinos could span the gamut of dark matter candidates. But here's the kicker: if they exist, they'd interact with ordinary matter almost exclusively through gravity, making them invisible to conventional detectors. The story of their birth reads like cosmic alchemy. In the universe's first trillionth of a second, during an era of exponential expansion called inflation, space itself might have rippled with quantum fluctuations. These tremors could have produced gravitinos in abundance, like sparks flung from a cosmic forge. Some theories suggest they arose from the decay of even heavier superparticles, raining down as stable end products of supersymmetry's cascade. Others propose they condensed directly from the primordial soup, their sheer stability locking them into the fabric of the cosmos. Yet for all their theoretical elegance, gravitinos are devilishly hard to pin down. Unlike WIMP or Axions, they wouldn't leave flashes in underground detectors or subtle distortions in magnetic fields. Their gravitational interactions are so feeble that a gravitino could pass through a planet as effortlessly as light through glass. Even their potential decay signatures, faint bursts of photons or neutrinos, would drown in the background noise of the universe. This elusiveness hasn't deterred physicists. Some hunt for gravitinos indirectly by studying the cosmic microwave background for imprints of their early universe behavior. Others look to high-energy colliders, where rare particle collisions might, for a fraction of a second, reveal supersymmetry's hidden architecture. There's even a wild possibility that gravitinos could alter how black holes evaporate, leaving subtle fingerprints in Hawking radiation. The gravitino hypothesis walks a tightrope between elegance and frustration. It ties dark matter to one of physics' most profound unification theories, yet offers few clear paths to confirmation. If gravitinos are real, they'd be more than just dark matter. They'd be living proof that space-time and quantum forces are woven together in ways we've barely begun to fathom. Until then, they remain one of cosmology's most tantalizing ghosts, particles that could solve everything if only we knew how to see them. What if dark matter isn't made of particles at all, but of cosmic magnets missing their other half? Enter magnetic monopoles, a concept so bizarre it sounds like science fiction, yet one that has haunted physicists for nearly a century. These hypothetical particles would be the magnetic equivalent of an electric charge, a north pole without a south, or vice versa, floating freely through space like rogue atomic fragments. While we've never spotted one, their existence is elegantly predicted by grand unified theories, frameworks that attempt to merge electromagnetism with the nuclear forces. And if they're out there, lurking in the vast dark halos of galaxies, they could be masquerading as the invisible mass we call dark matter. The story begins with symmetry. In our everyday world, magnets always come in pairs. Snap a bar magnet in half, and you'll still have two poles, not isolated ends. But in the searing heat of the early universe, moments after the Big Bang, the rules might have been different. As the cosmos cooled and fundamental forces split apart, topological kinks in spacetime could have frozen into existence, creating stable, solitary magnetic charges. These monopoles wouldn't just be curiosities, they'd be staggeringly dense, packing the mass of a proton into a space a billion times smaller. A single teaspoon of monopoles might outweigh a mountain, making them prime candidates for dark matter's gravitational heft. Galaxies could have swept these relics up over billions of years, trapping them in gravitational wells like cosmic flypaper. If monopoles are as abundant as some theories suggest, their collective weight would explain the missing mass tugging on stars and bending light. But here's the twist: monopoles wouldn't just sit there silently. Their magnetic nature means they'd interact in ways ordinary dark matter can't. Galactic magnetic fields might nudge them into dense filaments or sheets, subtly altering their distribution compared to cold dark matter's smooth halos. Some models even suggest monopoles could catalyze proton decay, a rare process where matter unravels, leaving faint but detectable traces in ancient water tanks buried deep underground. The hunt for monopoles has taken physicists from moon rocks to particle colliders. Experiments like MOEDL at the Large Hadron Collider have scoured high-energy collisions for monopole creation, while cosmic ray detectors search for their telltale ionization trails. There's even a chance they've been hiding in plain sight. Some theories suggest monopoles could have clustered into monopole nuggets, dense objects mimicking primordial black holes or neutron stars in gravitational surveys. What makes this idea so tantalizing is its dual payoff. Finding monopoles wouldn't just solve the dark matter puzzle, it'd validate grand unified theories and rewrite our understanding of fundamental forces. Until then, they remain ghostly specks on the edge of physics, a reminder that the universe's greatest mysteries might be hiding in the broken symmetries of creation. Forget particles altogether. What if dark matter is something far more fundamental, woven into the very fabric of space like an invisible cosmic tide? This is the radical premise of quantum field dark matter, a theory that trades discrete particles for a universe-filling field, humming with energy and sculpting galaxies through its oscillations. Picture the Higgs field, which grants particles their mass, but imagine a cousin to it, a shadowy counterpart that doesn't interact with light yet warps spacetime with its presence. Instead of clumps of invisible matter, this model proposes a dynamic, fluid-like entity that vibrates at specific frequencies, its peaks and troughs dictating where galaxies cluster and stars are born. The elegance of this idea lies in its simplicity. Fields are everywhere in physics. Electromagnetic fields guide light, gravitational fields bend spacetime, and quantum fields underpin every particle's existence. Dark matter as a field wouldn't need exotic new particles. It'd be an inherent property of the universe, like a silent note resonating through the cosmos. These oscillations could explain why galaxies form where they do. Where the field's vibrations are strongest, gravity would amplify, pulling ordinary matter into the dense knots we see as galaxy clusters. Where the field calms, vast cosmic voids would stretch empty. It's a cosmic orchestra where dark matter's unseen waves conduct the visible universe's structure. Critically, this framework tackles one of cold dark matter's biggest headaches, the too-big-to-fail problem. Simulations predict countless massive dwarf galaxies orbiting giants like the Milky Way, yet we observe far fewer. A quantum field's oscillations would naturally suppress these overdensities, smoothing out small-scale clumps while preserving larger structures. The field's inherent stiffness, resisting compression at certain scales, could also explain why galaxy cores appear less dense than predicted, sidestepping the need for complex self-interacting particles. Detecting such a field would require a paradigm shift. Traditional detectors hunt for particle collisions, but a field's influence would be subtler, a gradual warping of spacetime or faint distortions in the cosmic microwave background. Some proposals involve studying the precise timing of pulsars, whose regular beats might waver as the field's oscillations pass through them. Others suggest that ultra-precise atomic clocks, sensitive to minuscule changes in fundamental constants, could catch the field's ripple effects. Yet the boldest implication isn't just practical, it's philosophical. If dark matter is a quantum field, it blurs the line between matter and force, particle and wave. The universe's hidden scaffolding wouldn't be made of stuff at all, but of something more primal, a vibration, a rhythm, a fundamental tremor in the dark. As we peer deeper into the cosmos, this theory invites us to reconsider not just what dark matter is, but what it means to exist at all. For decades, the hunt for dark matter has focused on exotic particles and unseen forces, but what if we've been overlooking something far more familiar? Baryonic dark matter flips the script, suggesting that at least part of the universe's missing mass might be hiding in plain sight, disguised as ordinary matter we've simply failed to detect. We're talking about the same protons, neutrons, and electrons that make up stars, planets, and even our own bodies, just lurking in forms so elusive they've slipped under astronomy's radar. Take cold gas clouds drifting between galaxies. These vast reservoirs of hydrogen, chilled to temperatures just a few degrees above absolute zero, don't emit the vibrant light of stars or the searing glow of ionized plasma. Instead, they linger invisibly, detectable only when they subtly absorb the light of distant quasars passing behind them. Then there's the menagerie of failed stars, brown dwarfs too small to ignite nuclear fusion, or rogue planets cast adrift from their parent solar systems, wandering the cosmos like cosmic orphans. These dim, lonely objects could number in the trillions, their collective mass adding up to a significant fraction of the universe's missing baryons. But here's the catch: while baryonic dark matter might fill some of the gaps, it can't shoulder the entire cosmic burden. Detailed inventories of ordinary matter, based on precise measurements of the cosmic microwave background and the abundance of light elements forged in the Big Bang, reveal a stark mismatch. Even if we accounted for every rogue planet and every wisp of cold gas, visible baryons still fall short by a factor of 5 or more compared to dark matter's gravitational footprint. There's simply not enough ordinary matter, no matter how cleverly hidden, to explain why galaxies spin as fast as they do or why galaxy clusters bend light so dramatically. Yet dismissing baryonic dark matter entirely would be a mistake. Its existence forces us to confront how much we don't know about the ordinary building blocks of the cosmos. Consider the missing baryon problem. About half the normal matter predicted by Big Bang nucleosynthesis remains unaccounted for, even after tallying up stars, gas, and dust. Some theorists suggest this missing matter might be tied up in vast filaments of warm, hot intergalactic medium, a diffuse web of ionized gas too faint to spot with current telescopes. Others propose that primordial black holes forged from collapsing baryons in the early universe could bridge part of the gap. The lesson here is one of humility. Baryonic dark matter reminds us that before invoking entirely new physics, we must exhaust every possibility within the known laws. It's a cosmic detective story where the suspects aren't just exotic strangers. They're the usual players hiding in the shadows. And while ordinary matter alone won't solve the dark matter enigma, its hidden forms could still hold vital clues waiting to be uncovered by the next generation of telescopes and probes. After all, the universe has a habit of surprising us, often in ways we least expect. Imagine the universe as a cosmic mirage, a three-dimensional projection of information encoded on a distant, two-dimensional surface. This mind-bending concept, known as the holographic principle, might hold the key to one of dark matter's most perplexing secrets. Holographic dark matter proposes that what we perceive as invisible mass could actually be the gravitational shadow of data imprinted on the universe's farthest boundaries, like ripples from a pebble thrown into the void. It's a theory so speculative it borders on metaphysics, yet so mathematically compelling that physicists can't ignore its allure. The roots of this idea stretch back to black hole physics, where scientists discovered something astonishing. The entropy, or information content, of a black hole isn't proportional to its volume but to its surface area. This hinted at a radical possibility. Reality's true scaffolding might be lower dimensional, with our perception of depth and volume merely an illusion. Extend this logic to the entire cosmos, and you get holographic dark matter, an echo of boundary data manifesting as gravitational heft in our visible universe. Instead of particles or fields, dark matter becomes a cosmic glitch, a side effect of the universe's hidden coding. What makes this theory so tantalizing is how neatly it sidesteps the pitfalls of traditional dark matter models. No need to invent undiscovered particles or hidden forces. The missing mass emerges naturally from the geometry of spacetime itself. Picture a galaxy's rotation curve. Stars at the edge whip around faster than visible matter allows. In the holographic framework, this anomaly could arise from information on the cosmic horizon subtly warping local gravity, like a projector casting shadows that bend the rules of physics. Critics argue the idea is untestable, a beautiful abstraction with no clear path to verification. Yet subtle clues might lurk in the cosmic microwave background's polarization patterns or anomalies in gravitational lensing. Future space telescopes, like the European Space Agency's Euclid mission, could uncover statistical fingerprints of holographic effects imprinted on large-scale cosmic structures. The boldest implication: if holographic dark matter is real, the universe isn't just stranger than we imagined. It's a literal illusion, a hologram where darkness itself is the ink of a deeper reality's code. And that changes everything. What if dark matter isn't perfectly stable? What if it's slowly unraveling particle by particle, releasing faint bursts of energy as it decays? This is the provocative premise of dark matter decay, a theory suggesting that the universe's invisible scaffolding might be quietly disintegrating, transforming into photons, neutrinos, or even other exotic particles over cosmic timescales. Imagine an iceberg melting in slow motion, but instead of water, it's shedding invisible ripples of light and matter into the void. If true, this process could leave behind a subtle but detectable trail, one that might already be hiding in the gamma-ray glow of distant galaxies. The evidence comes from places like the center of the Milky Way, where telescopes have spotted an unexplained excess of gamma rays, a persistent, diffuse glow that conventional astrophysics can't fully account for. One tantalizing explanation: dark matter particles stacked densely in the galactic core could be annihilating or decaying into high-energy photons, producing this eerie signal. Similar anomalies appear in galaxy clusters and even the cosmic microwave background, where unexpected spikes in radiation might betray the slow disintegration of the universe's hidden mass. It's like finding faint smoke rising from an unseen fire, hinting at a process happening just beyond our perception. But how would decay work on a particle level? Take sterile neutrinos, for example. If these hypothetical dark matter candidates were unstable, they might decay into ordinary neutrinos and X-ray photons, a signature that aligns with observed excesses at specific energies. Other models propose that dark matter particles could split into pairs of gamma rays, leaving sharp spectral lines that stand out against the cosmic background. The key is the timescale. Decay would have to be sluggish enough for dark matter to persist over billions of years, yet frequent enough to produce the faint signals we're now detecting. The implications are staggering. If dark matter decays, it wouldn't just solve astrophysical anomalies, it would mean the universe's missing mass isn't permanent. Over trillions of years, entire galaxies could lose their gravitational anchors, their stars drifting apart as the dark matter halos that bind them evaporate. This puts a countdown clock on cosmic structure itself, albeit one ticking imperceptibly slowly. Yet the theory isn't without challenges. Distinguishing dark matter decay from other astrophysical processes like pulsars or black hole activity requires painstaking precision. Experiments like the Fermi Gamma Ray Space Telescope and upcoming observatories like the Cherenkov Telescope Array are refining their searches, hunting for telltale energy signatures or asymmetries in gamma ray distribution that could point to a dark matter origin. The beauty of this idea lies in its duality. Dark matter decay bridges the gap between particle physics and cosmology, offering a way to test theories not just through collisions in labs, but by reading the universe itself like a cosmic lab notebook. Whether the signals hold up or fade under scrutiny, one thing's certain: the universe's shadows are far more dynamic than we ever imagined. What if dark matter doesn't exist at all, and we've been misreading the universe's deepest rules this whole time? This is the radical proposition of modified Newtonian dynamics, or MUND, a theory that swaps invisible particles for a simple tweak to gravity itself. Instead of invoking vast halos of unseen matter to explain why galaxies rotate faster than expected, MUND suggests that gravity behaves differently at cosmic scales, subtly strengthening its grip where Newton's laws predict it should fade. It's a bold rewrite of physics' most familiar force, one that dares to ask, could our understanding of gravity be incomplete? The roots of MUND trace back to the 1980s, when physicist Mordechai Milgrom noticed something peculiar about galactic rotation curves. The outer stars of spiral galaxies whirl so fast that, under Newton's laws, they should fling into the void unless unseen mass anchors them in place. But Milgrom proposed an alternative. What if gravity doesn't weaken as sharply with distance as we thought? Instead of relying on dark matter's gravitational pull, MUND introduces a tiny adjustment. Below a certain critical acceleration, a threshold far gentler than Earth's gravity, the force of attraction tapers off more slowly, providing the extra tug needed to keep stars from escaping. This single tweak reproduces galaxy rotation curves with startling accuracy, no dark matter required. Where MACHOs shines brightest is in its predictive power. Take ultra-diffuse galaxies like Dragonfly 44, which appear almost transparent yet rotate as if packed with dark matter. Adjusted gravity neatly explains their motion without invoking invisible mass. Even more striking are tidal dwarf galaxies, clumps of stars born from galactic collisions. These structures, made purely of visible matter, move as if dark matter is present, yet MACHOs accounts for their behavior purely through modified gravity. It's as if the universe handed scientists a control group and MACHOs passed the test, but the theory isn't without glaring cracks, its biggest hurdle. The bullet cluster. When two galaxy clusters collided, their visible matter, a haze of hot gas, piled up in the center, while their gravitational lensing effects, which reveal mass distribution, stayed offset. This separation is a smoking gun for dark matter, which would sail through the collision unaffected. MACHOs struggles to explain this mismatch without some form of unseen mass. Critics also point to the cosmic microwave background, whose intricate patterns align exquisitely with dark matter models but demand cumbersome additions to fit MACHOs framework. Then there's the elephant in the room, relativity. Newton's laws are just a low-energy approximation of Einstein's theory, and MACHOs lacks a relativistic foundation that meshes with the broader universe. Efforts like TVS tensor vector scalar gravity attempt to bridge this gap, but they introduce layers of complexity that dilute MACHOs' initial elegance. Yet the allure persists. MACHOs defenders argue that dark matter's own shortcomings, the failure to detect particles after decades of searching, the messy adjustments needed to fit small-scale galaxy data, justify exploring alternatives. Perhaps gravity does play by different rules in the cosmic deep, where accelerations are imperceptibly faint. Or maybe the truth lies somewhere in between, a blend of modified gravity and some dark matter, a hybrid solution that splits the difference. What makes MACHOs so compelling isn't just its challenge to orthodoxy, it's the reminder that science thrives on dissent. Every anomaly, every stubborn discrepancy is an invitation to question assumptions. Whether MACHOs ultimately triumphs or falls, its legacy is secure. It forces us to confront the possibility that the universe's mysteries might not be hidden in the dark, but written in plain sight, waiting for us to read them anew. Imagine the universe as a vast sheet of ice, freezing so rapidly that cracks form in its surface, imperfections locked in for eternity. These cosmic cracks, known as cosmic strings, could be more than just relics of the Big Bang's fiery aftermath. They might be the hidden architects of dark matter itself. Unlike particles or exotic fields, cosmic strings are topological defects in spacetime, ultra-thin filaments of pure energy, thinner than a proton but stretching across billions of light-years. Their gravitational pull could explain why galaxies cling together, not through invisible particles but through the universe's own primordial scars. The concept springs from the early universe's chaotic phase transitions. As the cosmos cooled and fundamental forces split apart, electromagnetism peeling away from the weak force, for example, spacetime might have crystallized unevenly, leaving behind flaws in its structure. These defects wouldn't just be static blemishes, they'd be dynamic, vibrating strings with immense mass density. A single cosmic string just 1 light-year long could weigh as much as an entire galaxy, warping spacetime around it like a taut wire bending a bedsheet. What makes cosmic strings such compelling dark matter candidates is their gravitational footprint. Unlike diffuse halos of particles, strings would produce distinctive lensing patterns, double images of distant quasars or strange, razor-thin distortions in background galaxies. Some astronomers have even hunted for these signatures in high-resolution sky surveys, looking for telltale lines of warped light where strings might slice through our line of sight. The challenge: these effects would be vanishingly subtle, like spotting a spider's thread against the glare of a spotlight. Yet the most tantalizing clue might come from the cosmic microwave background. Cosmic strings, if they exist, would have left jagged imprints in this ancient light, telltale kinks or discontinuities in the temperature fluctuations. Experiments like the Planck satellite have scoured the data for such anomalies, though no smoking gun has emerged. Critics argue that cosmic strings, while elegant, struggle to account for dark matter's uniform distribution. Their gravity would be intensely concentrated along narrow filaments, not smoothly spread like the halos needed to explain galactic rotation. Still, proponents counter that a network of crisscrossing strings, a cosmic spiderweb woven in the Big Bang's aftermath, could collectively mimic the effects of particle-based dark matter, especially if smaller strings fragmented and evaporated over time. The wild card: cosmic strings might also be time capsules. If they looped or collided, they could have spawned bursts of gravitational waves detectable by observatories like LIGO or the upcoming LISA mission. Some theories even suggest these strings could seed supermassive black holes or trigger anomalous cosmic rays, offering multiple avenues for indirect discovery. Whether cosmic strings ultimately solve the dark matter riddle or fade into the annals of beautiful but unproven ideas, they remind us of a profound truth: the universe's hidden scaffolding might not be made of stuff at all, but of spacetime's own imperfections, frozen echoes of creation's first fractures. What if dark matter isn't just hiding in our universe, but trapped in another dimension entirely? This is the spine-tingling premise of Brainworld Dark Matter, a twist on the Kaluza-Klein theory that imagines our cosmos as a three-dimensional brain floating in a higher dimensional space, like a sheet of paper suspended in a vast, unseen void. In this scenario, certain particles could be stuck to this brain, like ink on paper, while others, including dark matter, might roam freely through the full expanse of higher dimensions, their gravity bleeding into our world while they remain forever beyond our reach. The idea springs from string theory's most audacious predictions. If extra dimensions exist, they could be compactified, curled up so tightly that we'd never perceive them directly, or vast enough to host entire shadow realms. Dark matter might be a particle that, by some quirk of physics, is confined to one of these hidden dimensions, unable to step onto our brain except through gravity's universal handshake. Picture ants crawling on a tablecloth. They're oblivious to the crumbs trapped beneath the fabric, even as those crumbs subtly dent the surface. In this analogy, we're the ants, and dark matter's gravity is the dimple we can't explain. But how would we detect something so fundamentally alien? Enter collider experiments like the Large Hadron Collider. By smashing protons together at nearly light speed, scientists might briefly create particles that carry momentum into extra dimensions, leaking energy from our brain in ways that defy standard physics. Missing energy signatures, where detectors record less energy than expected post-collision, could betray these fugitive particles. Similarly, gravitons, the hypothetical carriers of gravity, might oscillate between dimensions, leaving faint imprints in high-energy collision data. The real kicker: Brainworld Dark Matter could solve one of physics' biggest puzzles: why gravity is so weak compared to other forces. If gravity's strength is diluted because it spreads into extra dimensions, dark matter's elusiveness suddenly makes poetic sense. It's not ignoring us, it's operating on a plane we're literally not built to perceive. Critics argue that without empirical proof, extra dimensions remain speculative. Yet the math is compelling and the hunt is on. Experiments like the proposed Future Circular Collider could push energy thresholds high enough to probe these hidden realms directly. Until then, Brainworld Dark Matter stands as a breathtaking reminder. The universe's greatest secrets might not lie in the dark, but in the folds of reality we've yet to unfold. Our universe has a curious quirk: matter vastly outnumbers antimatter. For every billion particles of antimatter created in the Big Bang, there were 1,000,000,001 particles of matter. That tiny imbalance is why everything from stars to smartphones exists today. But what if dark matter follows the same twisted rule? Enter asymmetric dark matter, a theory suggesting that dark particles, like their visible counterparts, have antiparticles, and that some primordial process tipped the scales overwhelmingly in favor of one over the other. This idea isn't just cosmic symmetry for symmetry's sake. The parallels between dark matter's mystery and the matter-antimatter puzzle are too striking to ignore. Both problems boil down to missing mass, one in the form of invisible gravitational scaffolding, the other in the unexplained dominance of matter we're made of. Could the same mechanism that favored matter over antimatter, a process called baryogenesis, have also privileged dark matter over its mirror counterpart? The math suggests it's possible. Just as slight violations in physics symmetry laws led to our matter-rich universe, similar fractures in dark sector symmetries could have spawned an excess of dark particles, leaving their antiparticles to vanish into oblivion. Here's where it gets elegant. In many models, asymmetric dark matter isn't just a copycat of baryogenesis, it's directly tied to it. Imagine the early universe as a simmering cauldron where visible and dark matter were linked through shared forces. As conditions cooled, a phase transition could have simultaneously skewed the creation of both types of matter, like a cosmic seesaw tilting two imbalances at once. Some theories even propose that dark matter's asymmetry drove the visible matter excess, with the two sectors communicating through hidden interactions we've yet to uncover. The implications are profound. If dark matter carries an asymmetry like ordinary matter, it would need specific properties to avoid self-annihilation. Unlike WIMP, which rely on being stable but electrically neutral, asymmetric dark matter would have to lack antiparticles entirely, or have them vanish early on. This tweak could explain why dark matter seems so aloof. With no counterparts left to annihilate with, it simply lingers, its gravitational pull the only trace of its existence. Critics argue that inventing a separate asymmetry for dark matter complicates an already messy puzzle. Yet the theory's beauty lies in its economy. It doesn't just explain dark matter's abundance, it ties it to one of cosmology's deepest questions, suggesting that the visible and invisible universe might be two sides of the same skewed coin. Experiments hunting for neutron oscillations or primordial gravitational waves could soon test these ideas, probing whether nature's imbalances are truly a shared flaw in the cosmic fabric. Whether asymmetric dark matter holds up or not, it forces us to confront a humbling truth. Our universe's structure might hinge on broken symmetries we're only beginning to grasp, tiny cracks in reality's rules that made all the difference between a void and a world teeming with galaxies, planets, and life. For decades, neutrinos have been the universe's most notorious shape-shifters, particles that oscillate between flavors as they streak through space at nearly the speed of light. But what if this quantum chameleon act holds the key to dark matter's identity? Enter the tantalizing possibility of sterile neutrino mixing, a theory where dark matter isn't just hiding in the shadows but slipping in and out of our detectable reality through fleeting interactions with its more sociable neutrino cousins. Sterile neutrinos are the hypothetical rebels of the neutrino family. Unlike their ordinary counterparts electron, muon, and tau neutrinos, which occasionally bump into matter via the weak nuclear force, sterile neutrinos would interact solely through gravity, making them nearly impossible to catch. Yet here's the twist: if sterile neutrinos can oscillate into regular neutrinos and back again, even briefly, they'd leave behind faint but measurable ripples in experiments designed to study neutrino behavior. It's like spotting a ghost by the way it momentarily distorts the air around it. The first hints of this phenomenon emerged from an enigma called the reactor antineutrino anomaly. Nuclear reactors produce vast streams of electron antineutrinos, and scientists can predict how many should appear at detectors a certain distance away. But something's off. Measurements consistently show a shortage, as if a fraction of these antineutrinos vanished en route. One compelling explanation: they didn't disappear, they transformed, oscillating into sterile neutrinos that detectors can't see. Similar anomalies popped up in calibration experiments with radioactive sources, where neutrino counts fell short of expectations. Together, these discrepancies form a pattern that sterile neutrino mixing could neatly explain. But how would this connect to dark matter? If sterile neutrinos are heavy enough, say, a few kiloelectronvolts, they could have piled up in the early universe, their sheer numbers accounting for the gravitational glue holding galaxies together. Their occasional oscillations into regular neutrinos would make them detectable indirectly, like a thief leaving fingerprints at the scene but never showing up on camera. This dual identity solves two puzzles at once: dark matter's dominance and the reactor anomalies that defy standard neutrino physics. The hunt for these elusive oscillators is underway. Experiments like Mini Bueni at Fermilab and Dance near Russian reactors are scouring neutrino beams for excess events, extra flashes of light, or unexpected energy distributions that could betray sterile neutrinos' presence. Even more ambitious projects, like the upcoming Juno detector in China, aim to pin down oscillation patterns with unprecedented precision. Meanwhile, telescopes like Chandra and XMM Newton are scanning the cosmos for X-ray signatures that could reveal sterile neutrinos decaying in distant galaxy clusters. Critics point out gaps, of course. The reactor anomalies might stem from calibration errors or incomplete nuclear physics models rather than new particles. And sterile neutrinos light enough to mix significantly struggle to explain all of dark matter's gravitational effects without tweaking cosmological models. Yet the theory's elegance keeps it alive. If sterile neutrino mixing is real, it would weave dark matter into the same quantum tapestry as the standard model's most enigmatic particles, a hidden thread connecting the visible and invisible universe through the subtle, subatomic dance of oscillation. The stakes couldn't be higher. Discovering sterile neutrinos wouldn't just crack the dark matter mystery. It'd force us to rewrite the rules of particle physics, revealing a universe where even the most aloof particles are secretly in conversation with the world we know. Until then, every anomalous neutrino count, every unexplained X-ray whisper is a potential clue, a fleeting glimpse of darkness flickering into light. Picture the early universe as a seething cauldron of particles, so dense and hot that matter and energy were constantly colliding, annihilating, and recreating each other in a frenzied dance. In this primordial soup, dark matter particles wouldn't have been solitary, they'd have been social, frequently bumping into their own antiparticles and vanishing in flashes of energy, only to be reborn from the chaos. But as the cosmos expanded and cooled, something dramatic happened. These particles suddenly found themselves frozen in time, cut off from their explosive partnerships. This moment, known as thermal freeze-out, is the cornerstone of one of the most compelling dark matter theories. The idea that what we call dark matter today is nothing more than the cosmic leftovers of this ancient cooling process. Here's how it works. In the universe's first microseconds, dark matter particles and their antiparticles were in thermal equilibrium, meaning their creation and annihilation rates were perfectly balanced, like a crowded room where people constantly pair off and exit, while new arrivals stream in just as fast. But as the universe expanded, temperatures plummeted, and the energy available for creating new particle pairs dropped below a critical threshold. Suddenly, the annihilation process couldn't keep up. Particles that once vanished in bursts of energy now had no partners left to collide with. They were stranded, their numbers frozen at a fixed density, drifting through a cooling cosmos like unclaimed dance partners when the music fades. The math behind this process is startlingly precise. For freeze-out to leave behind the exact abundance of dark matter we observe today, these particles must have a very specific interaction cross-section essentially, a measure of how likely they were to collide and annihilate in the early universe. Remarkably, when physicists calculate this value for weakly interacting massive particles WIMP, they land on a number that aligns perfectly with the predictions of supersymmetry, the theoretical framework suggesting every known particle has a heavier twin. It's as if the universe left us a numerical breadcrumb trail, a cross-section around 10^2 cubic centimeters per second, often called the WIMP miracle, because it emerges naturally from independent physics with no fine-tuning required. But freeze-out isn't just a theoretical curiosity, it leaves fingerprints we can hunt for. If dark matter particles were once sociable enough to annihilate frequently, there's a chance they might still occasionally collide today, especially in regions where they're densely packed like galactic cores. These rare interactions could produce faint bursts of gamma rays or other high-energy particles. Experiments like the Fermi Gamma Ray Space Telescope have spent years scanning the sky for such signals, particularly from dwarf galaxies, where minimal stellar activity makes it easier to spot dark matter's potential whispers. Yet the freeze-out scenario isn't without its puzzles. If dark matter is a thermal relic, why haven't we detected WIMP directly in underground labs like Xenon or LUX? Some theorists argue we might be searching for the wrong mass range, or that interactions are rarer than expected. Others propose alternative freeze-out mechanisms like forbidden dark matter, where annihilations require rare, high-energy collisions that shut off abruptly as the universe cools. There's even the possibility of multi-component dark matter, where several particle species froze out at different times, creating a mix of invisible ingredients that collectively shape galactic gravity. The beauty of the thermal relic idea is how deeply it ties dark matter to the universe's infancy, those ghostly particles streaming through your body right now. They're not just passive spectators, they're cosmic survivors, relics of an era when the entire universe was hotter than the core of a star. And if we can decode their story, it wouldn't just solve the dark matter mystery, it'd give us a backstage pass to the very first moments of existence, when the laws of physics were writing the script for everything to come. Most of us think of crystals as delicate, glittering structures, snowflakes, gemstones, maybe even the quartz in your watch. But imagine a crystal unlike any other, forged not from atoms but from the universe's most elusive substance, dark matter. Picture vast, sprawling lattices of invisible particles, silently locking into place across galactic halos like cosmic ice forming in the void. This isn't science fiction, it's the daring hypothesis of dark matter crystals, a theory that dares to ask, what if the universe's hidden mass isn't just a chaotic haze, but an ordered, almost architectural framework shaping the cosmos from within? The idea starts with a simple yet radical shift in perspective. Most dark matter models assume particles drift freely, interacting only through gravity's faint tug. But if dark matter has even a whisper of additional forces, some hidden counterpart to electromagnetism, these particles could organize into repeating patterns like atoms aligning in a diamond. These wouldn't be crystals as we know them. Forget sparkling facets, dark matter crystals would be colossal, their unit cells stretching light years across, their structure detectable only through the subtlest gravitational whispers. How could something like this form? Just as earthly crystals nucleate around imperfections, a speck of dust, a microscopic flawed dark matter crystals might have grown from quantum ripples in the early universe. Regions where dark matter particles clustered slightly denser could have acted as seeds, their mutual attraction overcoming the chaos of expansion. Over billions of years, these patches might have stabilized into lattices, locking into place as the cosmos cooled. The result, galactic halos threaded with invisible scaffolds, their rigid geometries subtly warping the motion of stars and gas. Here's where things get even wilder. These crystals wouldn't just sit there, they'd sing. Every jostle, every collision between galaxies could send vibrations ringing through their lattices, releasing low-frequency gravitational waves. Unlike the high-frequency chirps from black hole mergers, these signals would be deep, resonant hums, lingering for years or even centuries. telescopes like LISA, the upcoming space-based gravitational wave observatory, might one day catch these echoes, tuning into the universe's hidden symphony. But why would we even consider such a bizarre possibility? The clues lie in the anomalies. Some galaxies rotate with unexpected smoothness, their outer stars moving in lockstep rather than slowing down as standard models predict. Dark matter crystals could explain this. Their ordered structure might distribute gravity more evenly than a loose halo of particles. Then there's the too big to fail problem. Simulations predict more massive dwarf galaxies than we observe. A crystalline dark matter framework might suppress small-scale clumping, pruning excess dwarfs like a cosmic gardener. Of course, skeptics pounce on the big question: what force could possibly bind dark matter into crystals? One compelling answer comes from theories of a dark photon, a hidden carrier of interaction akin to light, but exclusive to the shadow realm of dark matter. If dark photons exist, they could mediate short-range forces between particles, allowing them to arrange into regular arrays. Another possibility is that dark matter particles themselves have intricate structures, like composite atoms with nested orbits, enabling complex bonding. The implications are staggering. If dark matter crystals are real, they'd redefine our understanding of galactic evolution. Merging galaxies might shatter these invisible lattices, scattering shards that later reform, a cycle of destruction and rebirth playing out in the dark. Supermassive black holes could drag crystalline halos into swirling vortexes, warping spacetime in ways no particle-based model predicts. Even cosmic voids, those vast empty regions between galaxies, might owe their expanse to dark matter's rigid geometry, its structure resisting collapse where ordinary matter would crumple. Yet the true test lies in the hunt for those ghostly gravitational waves. Unlike impulsive bursts from colliding neutron stars, dark matter crystals would produce persistent, almost melodic frequencies, a hum reverberating through the fabric of spacetime. Detecting them would require patience and precision, like listening for a tuning fork's note in a hurricane. But if we succeed, it wouldn't just confirm a new form of dark matter. It would unveil a universe far more structured, more artful than we ever dared to dream. A cosmos where even the darkness has its own hidden order, its own silent rhythm. Imagine if dark matter isn't some exotic particle or hidden force, but a ghostly illusion, a side effect of spacetime's deepest workings. This is the mind-bending premise of emergent dark matter, a theory that flips the script entirely. Instead of searching for unseen stuff, it suggests dark matter is more like traffic jams or ocean waves phenomena that emerge from countless smaller interactions, not because of any single ingredient, but because of how the system behaves as a whole. Think of it like temperature. We talk about it every day, but temperature isn't a thing. It's a collective property emerging from the frenzied motion of atoms. A single molecule doesn't have a temperature. It's only when you have trillions of them jostling together that the concept even makes sense. Emergent dark matter proposes something similarly radical. What if the gravitational effects we blame on invisible matter are actually spacetime's way of averaging out deeper, more fundamental physics we haven't uncovered yet? The math behind this idea pulls from the strange world of condensed matter physics, where simple rules at microscopic scales give rise to bizarre behaviors en masse. Electrons in a metal, for example, can collectively act as if they're a single particle with a different mass altogether, a quasi-particle. Apply this logic to spacetime itself, and you get a wild possibility. The extra gravity attributed to dark matter might be the universe's way of smoothing out tiny, unseen fluctuations in the fabric of reality. It's not that spacetime is being warped by hidden mass, it's that spacetime, when viewed at cosmic scales, behaves as if there's extra mass even when there isn't. This isn't just philosophical hand-waving. Some theories, like Eric Verland's emergent gravity, suggest that dark matter's pull could arise from entropy, the same principle that makes heat flow from hot to cold. In this view, gravity isn't a fundamental force but an entropic force, a statistical tendency for systems to evolve toward disorder. When you calculate how this plays out across galaxies, you get equations that mimic dark matter's gravitational effects without needing any invisible particles. It's like realizing the shadow you've been chasing isn't a monster, it's just the way the light happens to fall. Of course, critics pounce on the gaps. Emergent dark matter struggles to explain all the evidence at once, like the precise lensing patterns seen in galaxy clusters or the cosmic microwave background's intricate fluctuations. Yet its allure is undeniable. It reframes dark matter not as a missing puzzle piece, but as a hint that the puzzle itself is far stranger than we thought, a cosmic optical illusion woven into the geometry of existence. If true, it wouldn't just solve a mystery, it would rewrite our understanding of reality, revealing a universe where even gravity is just the tip of an iceberg we've barely begun to chart. From WIMP to Axions, primordial black holes to mirror universes, we've ventured through a labyrinth of possibilities, each more daring than the last. Yet here's the humbling truth: after decades of research, countless experiments, and enough theoretical models to fill a galaxy, dark matter remains as enigmatic as ever. This isn't a failure of science, it's a testament to the universe's boundless creativity. The sheer diversity of theories 30 and counting reveals something profound. We're not just hunting for a missing particle. We're grappling with the very fabric of reality, probing the edges of known physics and rewriting the rules as we go. Consider how far we've come. A century ago, astronomers noticed stars orbiting galaxies too fast and called it a discrepancy. Today, we've mapped dark matter's gravitational fingerprints across the cosmos, from the bending of starlight to the cosmic web's vast architecture. We've built detectors in abandoned mines, repurposed particle colliders as cosmic microscopes, and turned entire galaxies into laboratories. Every null result, every tantalizing blip, every ruled-out theory isn't a dead end. It's a signpost narrowing the path toward truth. The next chapter promises even greater revelations. Projects like LUX Zeppelin are pushing detector sensitivity to unprecedented levels, while the Vera Rubin Observatory's legacy survey of space and time will scan the skies for dark matter's subtle distortions. The James Webb Space Telescope might spot the infrared glow of decaying sterile neutrinos, and future gravitational wave observatories could catch echoes of dark matter crystals vibrating in the void. Even quantum computers are joining the hunt, simulating exotic dark matter behaviors no lab could replicate. So here's where you come in. Which theory resonates with you? The elegant simplicity of WIMP, the haunting beauty of mirror matter, the audacious fluidity of superfluid dark matter. Drop your favorite in the comments, because this isn't just a puzzle for scientists in lab coats. Dark matter belongs to all of us, a shared mystery written across the night sky. Stay curious, stay skeptical, and above all, keep looking up. The universe has kept its greatest secret hidden for 13 billion years. But secrets, no matter how vast, aren't meant to stay buried forever.